Welcome back, students. Let us solve the same numerical by considering that the tendon is eccentrically placed, or it is placed at an eccentricity at 200 mm above the bottom fiber. All the rest of the data remains the same. We are not changing anything. Only thing, the case is different. In first case, previous case that we discussed, in that the tendon was concentric, that it was at CG. Now the tendon is eccentric and located at 200 mm above the bottom fiber. So the concept remains the same, the procedure remains the same, but we will have to find out what is the movement that is generated or that is created due to this eccentricity E. Okay, so here it is eccentric tendon. So we need to first find what is the eccentricity E. So the tendon is placed at 200 mm above the bottom fiber. So if this is the section and this is the CG, it is provided at 200 mm above the bottom. So we have to, this is eccentricity E. This is E. So it will be, this is 300, that is half of the section of 600 mm. So it is 300. So eccentricity will be 300 minus 200. So eccentricity E is nothing but 300 minus 200 mm, that is equal to 100 mm. So eccentricity we have got. Now we will have to find out what are the final stresses at midspan and at extreme fibers, or that is at the end section. We have already discussed the equation for the final stress when the tendon is eccentric. I will just repeat that. It is F, which is taken as F dash plus FB, where F dash is again a addition of F1 and F2, where F1 is the stress due to the tensile or due to the pre-stressed force, that is T by A. This is the stress, this is the first initial one which we were taking. So F1 is nothing but T by A, that is stress due to pre-stressing force, and F2 is the stress created due to movement due to eccentricity, which is equal to T into E by I into Y. We have already discussed this in previous lectures. I am just repeating it. So F2 is movement due to eccentricity E. So it is equal to T, that is the tensile pre-stressed force, into eccentricity upon I into Y. FB is due to the movement at the midspan, that is due to the loading, that is due to the UDL that is acting on the beam, external loading, which is M by I into Y. This also we have already discussed. So it is nothing but F is equal to F dash plus FB, where F dash is addition of F1 plus F2 and FB is nothing but M by I into Y. So let us start solving this numerical. Considering E we have already calculated, that is equal to 100. So first we will find out what is F dash. Okay, let us find out what is F dash, which is equal to F1 plus F2. Okay, so F1 is nothing but T by A. T we have already calculated in the previous equation. It is given, it is equal to 1920. I am using the same numerical values what we have used in the first numerical. So in case if you've missed onto something, please refer to the first numerical again. So area we have calculated, it is 400 into 600, that is equal to 240000, which is equal to 8 Newton per mm square. This is the same. Okay, that is F1. Now F2 is T into E by I into Y. T is 1920 into 10 raised to 3. Eccentricity E value is 100 divided by I is 72 into 10 raised to 8. We have already calculated this in the previous numerical, and value of Y is 300, same as what we have used earlier. So here the value is again 8 Newton per mm square. Therefore, F dash is equal to 8 minus or plus 8 Newton per mm square. This is how it is written. So again, this is either negative or positive depending on the tension and depending on the compression that happens. So F2 will be, now let us discuss what will be tensile and what will be compressive here. On that this sign convention will depend. F2 will be tensile at top and compressive at bottom. Why? Because at the bottom there is the tendon that is already available. So there will be a tensile force that will be exerted here, but it is going to experience compression after the loading. So there will be compressive force at the bottom and tensile force at the top. So this value of F2 will be tensile at the top and compressive at the bottom. That's why we write it as negative and positive. Negative for tension and positive for compression. So we first write tensile negative on top and positive at the bottom. So this sign convention will tell you where it is tensile and where it is compressive. Now let us find out what is the moment at the end section. So this is for the previous one. I will just delete this. Okay. So stress distribution at end section. Again, bending moment at the ends is equal to 0. Okay. And F, that is the final stress, will be equal to 8, or I will write it in terms of F dash and FB. Final stress will be equal to F dash plus FB, where F dash is nothing but F1 minus or plus F2 plus FB. Value of F1 is 8 minus or plus 8 and FB is equal to 0. That is, bending moment is 0, so value of FB also will be equal to 0. So here it is going to be 0 or 16. So either 8 minus 8 it will be 0 or 8 plus 8 it will be 16. So let us draw the stress diagram. So first F1, let us draw F1 first. This is A, that is F1, and it is 8. Okay, value of F1 is 8 and it is positive. This is only due to the pre-stress force, that is P by A. Then let us draw F2. F2 is tensile at the top and compressive at the bottom. So the diagram will be something like this. This being 8 negative and this being 8 positive. Okay. See, FB, that is this portion. It is just going to be a straight line because both the ends the moment is going to be 0. And D is F, that is addition of all the three, this plus this plus this, it will be something like this. So it is 8 minus 8, it is going to be 0, and it is 8 plus 8, it is going to be 16 here. Okay, so where this particular value is 300 mm, that is at the center from the top, 600 divided by 2. Now, where is T acting? Previously it was at CG, but now it is 100 mm below the CG. So this is the value of T. Similarly, we have already calculated the position of compressive force in the previous numerical, and that also is acting at 100 mm below the or towards the compressive side. It was actually above in the previous section, now it is going to be bottom because this is the compressive side. Earlier this was the compressive side and this was the tensile side. Now because this is the compressive side, the compressive force also is going to act below the neutral axis, below the CG, and again it will be at 100 mm. So here the line of action of C and T coincides. So there is no couple. It will be equal to 0. So there won't be any movement here, but that couple will be equal to 0. There won't be any couple that will be formed because there is no distance, because the line of action of C and T is same. Okay. So because of this eccentricity, this movement becomes 0. So this is the stress distribution at the end of the section. Now let us see what is the moment distribution at the midspan of the section. Again the concept remains the same, but only thing here what will change is there will be a midspan moment. So at midspan, again the equation that is for final stress is equal to F equal to F dash plus FB, where F dash is F1 minus or plus F2, which is going to remain the same as the previous one. Okay, so which is equal to 8 minus or plus 8. So I am not solving it again. F dash remains the same what we have done in part A, that is this. So here F dash we have already calculated. So it is F1 minus or plus F2. Now let us find out what is FB. FB is nothing but M by I into Y, where M is the midspan moment. We have also calculated this in the first numerical. I will just rewrite it. 192 into 10 raised to 6 divided by 72 into 10 raised to 8 into 300. This M is nothing but W into L by 8, where W is 265 and all. Y we have already calculated. I also is BD cube by 12. Okay, so with this you get this value as plus or minus 8 Newton per mm square. Therefore, the final stress F will be equal to 8 minus or plus 8 plus or minus 8, where this is F1, this is F2 and this is FB. So this means that the stress at the top fiber, the stress will be equal to 8 minus 8 equal to 0 plus 8. So at top fiber it will be 8 minus 8 plus 8, which is equal to 8 Newton per mm square. At bottom fiber it will be 8 plus 8 minus 8. So it is 8 plus 8, 8 plus 8 minus 8, which will be 8 again. It is 16 minus 8, 8. And here it is 0 plus 8, it is 8. So at the top fiber and at the bottom fiber, the stress remains the same, that is equal to 8 Newton per mm square. So you can note here from the numerical 1 and numerical 2 that if you change the position of the tendon, that is if you provide it at some eccentricity, the extreme fiber stresses in concrete gets reduced. Previously stresses in extreme compressive fibers were 0 and 16 Newton per mm square, but now it has been divided and it has been distributed equally on top and bottom, just because we have provided the same tendon at an eccentricity of 100 mm. So it has been reduced to 8 Newton per mm square from 16. So here we can conclude that if you just change the position of the tendon or you provide it at at some eccentricity E, then the stresses in the concrete gets reduced. Okay. So this is the final stress diagram for midspan stress, that is F1, this remains the same, F2, this also remains the same, FB is compressive on top and tensile at the bottom. So final stress will be 8 minus 8 plus 8, it will be 8, and 8 plus 8